Okay. So, in the previous videos, we talked about the density function rho and its ensemble average, how it is connected to the experimental values and all that. So now we will, for the couple of videos now, we will discuss about how this density function behaves fundamentally in a microcanonical ensemble. Okay. So in that connection, the the formulation or the theorem is generally called the Liouvilles theorem. Li is pronounced as Liouvilles. Liouvilles. So Liouvilles theorem, to the best of my understanding, it is basically applicable only for the microcanonical ensembles. But there are literature available where they try to apply it for canonical ensemble, which I couldn't really appreciate it that much. But in any case, this theorem is applicable for the microcanonical ensembles. So let me first of all state the theorem, and then we will explain it, and then we will go into the derivation, and then we will have detailed discussion on the significance of this theorem. That's the plan. So this Liouvilles theorem states that the total rate of change of density function right of QPT in the vicinity of any selected points of any system as it moves through the phase space is 0. Okay, so let me read it once more. So the Liouvilles theorem states that the total rate of change of density function in the vicinity of any selected point of any system as it moves through the phase space is 0. Phase space is also called the gamma space. So in some places you will see something like this, gamma space. It's one and the same thing. So basically it is telling that at some specific situations, as this density function moves through the phase space, it must obey d rho by dt is equal to 0. So that is what the statement is talking about. So basically, first and foremost, I would tell that this will imply that the density of a group of phase points, right? You have since the rho is not going to change with time as it moves through an ensemble, as it moves through a system which is in the phase space. It means that the density of a group of phase points will remain constant along the trajectory in the gamma space. It implies that the density of a group of phase points remains constant along their trajectory. What is the meaning of trajectory? Their path, right? Along their path. Trajectories in the gamma space. So this theorem implies that, so this is the statement, and this is the implication, fundamental implication. The density of a group of phase points remains constant along their trajectory in gamma space. So there's a very interesting similarity, which interesting analogy, which many textbooks, including that of Part1, talks about. So it projects a situation where this the movement of the representative points, or the distribution of the representative points, moves in the phase space like an incompressible liquid. So you have a distribution of representative points. So each representative points represents what? Microstate. So there is a distribution of representative points, and it moves in the gamma space like an incompressible liquid, right? What is rho? Rho is basically showing the distribution of representative points in the system, right? So here now we are telling that the d rho by dt is equal to 0, right? So which means that this so-called distribution of representative points, which is rho, moves in the phase space like an incompressible liquid, right? An incompressible liquid, you cannot change anything inside because it's incompressible already. Everything is fixed, right? So this is the implication of that. And as I understand, this is applicable only for the microcanonical ensemble. Now we will do the derivation in the next video, right? And then we will have more detailed discussions of the implications or the significance of the Liouvilles theorem.